Hey, my name is Yaron Fine. I'm a developer on the JavaScript API. Um, I'm part of the team who's building the rendering engine of the 2D API. Together with Dario, who's also with me on the team, we'll go through the process of building custom visualization using WebGL and 2D map views. We'll explain the technique. We're going to talk about some reason to use this technique, and we're going to have a walkthrough going through a implementation. And then Dario is going to talk about integrating a third-party rendering engine into the API using a custom layer and a custom layer view. The question is why custom layer? So there's many reasons. Primarily, if the user has specific visual requirements that are not supported with the out-of-the-box implementation, or if there's a need to have fine-grained control over the rendering, the visualization, or any other aspect of the data need to be rendered into the in the map. There's some need to integrate with third-party libraries or data formats that are not necessarily supported with the out-of-the-box API. Maybe some performance, specific performance requirements that again cannot be met with the out-of-box layers. And then brings to the question of why a layer. A layer is a well-known concept in GIS. When a layer is implemented, the user can turn it on, turn it off, move it around, under or above other layers in the map, can add support for heat testing, and recently added also, even if it's a custom layer, blend modes and new layer effects can be applied to that layer in the map. Um, in the JavaScript API, we distinguish between a layer and a layer view. A layer represents the data. It allows the user to save, to load the data, to export it, to exchange if it's part of the web map spec and such. And the layer view is responsible for the visualization or drawing the data itself. When implemented a custom layer, the developer is responsible for both implementing the layer and the layer view. We also provide some helper APIs to simplify the process, primarily dealing with WebGL, dealing with transformations, and so on. I'm going to hand it over to Dario to talk about the technique itself, what classes need to be implemented, what possibilities we have, what methods need to be implemented, and so on. When Dario is done with that part, we're going to do a walkthrough.
Thank you, Yaron. The JavaScript API provides two extensions points for writing custom layer views. The first one uses the Canvas 2D API and can be accessed by subclassing base layer view 2D. The other one uses WebGL and class base layer view GL2D. Which one to use depends on the visual requirements, performance requirements, the availability of third-party libraries, and the expertise of the developer. Today, we will focus on the WebGL case. The first choice that the developer needs to make is whether to use tiling or not. Then the developer can proceed to subclass layer. If using tiling, a tiling info should be specified on the layer. Then the developer needs to subclass base layer view GL2D and implement a few methods, some of which are optional. If tiling is in use, then the tiles changed method must be implemented. This is an example of subclassing layer. At the very least, the developer needs to implement create layer view that must return an instance of the subclassed base layer view GL2D. This is also where additional properties and methods can be added to the subclassed layer. In order to opt into tiling, simply define a tile info property. The API will maintain for you a list of coverage tiles that are required to cover the current extent. The subclassed base layer view GL2D instance will receive a tiles changed event every time that the coverage changes. This is the skeleton of a subclassed base layer view GL2D. At the very least, the developer needs to implement attach, detach, and render. Optionally, implementing heat test enables interactivity and the ability to programmatically query the layer view using screen space coordinates. Please note that attach, detach, and render are the only places from which it is allowed to call WebGL methods. Calling into WebGL from anywhere else, for instance the constructor, methods changed event, the heat test method, a timer or promise callback, is likely to corrupt the WebGL state and can possibly break the entire map view. The attach method acts as a constructor and has access to the map view's WebGL context through the this.context property. The attach method is typically used for WebGL resource creation. Not all resources are necessarily created in the attach method. Other resources can be created and destroyed dynamically in the render method as needed. On the other hand, creation of non-WebGL resources can be done in the actual constructor. The detach method acts as a destructor. It must destroy any WebGL resource that was created in attach or in render and cancel any pending operation. The render method is where actual rendering happens. It is called every frame. The render method receives a render parameter object containing the WebGL context, a stationary flag that tells whether the user is panning, zooming, or rotating, and a view state that completely defines the portion of the map that is displayed. At every frame, it must render the layer data based on the current view state by sending WebGL commands to the context. Note that when render is called, the WebGL state is guaranteed to be almost the default one. This ensures that you can write your rendering code against a well-specified initial state. However, the two settings that are not default are the bound frame buffer and the viewport. Your render method needs to render in that frame buffer with that viewport for your visualization to properly display and align with the rest of the layer stack and the base map. If you do bind another frame buffer or change the viewport, you need to bind the correct one by calling this bind render target and do a final composition step there. As mentioned before, you can optionally implement heat test to enable interactivity. The heat test takes a point in screen space and returns a promise to a graphic. If your layer really deals with graphics, pick a suitable one that is under the supplied coordinates and return that. Otherwise, you may have to synthesize a temporary graphic. Anyway, to enable automatic pop-ups, the returning graphic must have a source layer property that points to the custom layer. As a convenience for the developer, base layer WebGL2D exposes some function to tessellate geometries. This is the process that converts the geographical paths in the rings into actual triangles that WebGL can render. If your visualization needs to render lines and polygons, these methods are definitely worth checking out. This concludes this brief overview of the base layer WebGL2D class. Check out the documentation on the SDK website for more information. Back to you, Yaron, for your walkthrough.
So this is a walkthrough showing implement a custom layer and the layer view that render dynamic items, cars in this case, called tracking cars. I'm going to start with running the demo. Notice I'm opening the test app. It's building as a series of apps that render the layers. In this walkthrough, we're gonna focus on the first demo, which is basically just the code that render the cars, but this demo has more. The second demo shows the technique of highlighting cars, and it is doing through a post-processing effect. And then the third version is doing both, visualization and the highlight, but moves the logic itself and the connection to the WebSocket over to a web worker. If I'm launching the demo, and of course I'm going to launch the most advanced demo, even though we're going to only focus on the drawing itself. And notice it's loading. The service itself is already running. This is not the service, but the service is already running. It is basically a fake service. It's reading a feature layer, and it is and depending on the number of observation that the user has, you simply add those items and move them along. So here we have 10,000 items, in this case cars. The implementation is moving each item every 60 milliseconds. So if you zoom in, you'll see how smooth those items are moving. Again, this is 10,000 items. Each car is moving every 60 milliseconds. So there's lots of updates. We also added support for highlighting. Of course, this is random. Every few seconds, the service chooses a different set of cars to highlight. Um, so that is basically the idea. But one more thing that is supported is heat testing. I can simply hit a car and I'll show you in this case the car ID, the type, the heading. This is though given in radians. So excuse me for that. But so it's implementing like any other layer, and also in this particular version also added a out of the box layer effect, drop shadow in this case, just to make things a little nicer, I guess. Notice that as I'm zooming in and out, the code is scanning just to touch the cars, just to make the look a little nicer. It's not significant scaling, even though this is also doable. So that is really the demo. The source for both the stream service and the app is available in the public Git repo. These are the links. So you can, if you want, you can go get it. You can modify the app. You can use it for other purposes and so on. So the objective in this particular case is to implement those cars. It's consuming a dynamic feed. The feed is given through a WebSocket. And then to render those cars on the map, supporting heat testing. In this case, notice we also had support to a mechanism to show the highlight, or what we call active cars. Some consideration. The data is extremely dynamic. Each car is being updated multiple times a second. In terms of requirements, we only render those cars. So we're only rendering markers, or really points. We've got different types of cars, so we need to symbolize them differently. So we're not using a single symbol. We need to be able to scale the data as we zoom in and out a little bit. And then, of course, when we need to make sure that the data itself is anchored properly to its geographical position. So if we zoom and pan, we don't want things to start wiggling. This is important in this particular case. As far as implementation alternatives, we really have two. One is using tiles. The other one is not use tiles, basically use just a single WebGL buffer encoding all the data. Using tiles is actually pretty convenient, and it solves a lot of problems. As a matter of fact, in last year's presentation, we talked quite a bit about tiles. Tiles provide multiple level representation of the data. It works really well with lines and fills that those multiple level representation allow us to simplify the data and avoid artifacts. When we're using tiles, we can encode the data in integers. It saves a lot of GPU memory. As a matter of fact, we're using short integers. It also gives us a very good balance between the actual data and also the memory that we upload over to the GPU, because, well, if we only upload the data to the visible tiles, then we don't need to upload any other data to the GPU. So only the area that of interest is really the data that gets uploaded to the GPU. And of course, wraparound is also trivial when using tiles, but using tiles also has some drawbacks. Maintaining the data require dealing with complex data structures, primarily R trees or quad trees or other such complicated data structures. Because we need to distribute the data to the right tiles, so we need to figure out where each tile falls and which feature pertain to each tile. Dealing with z-order can be a problem. And we need to make sure not to that features are not being clipped at edge of tiles. Updates are extremely CPU and GPU intensive because imagine that we need to move items, so we need to remove the given item from one tile and into a secondary tile. Of course, that those tiles may already have some other features in them, so we need to maintain the Z order. So it's becoming quite a complex and heavy operation. Using a single buffer, it's simple, just single buffer. So we don't really need complex data structure or spatial data structure to maintain in order to render this data. We can use very few draw calls, to do the drawing. Updating is pretty simple to the point where it can become almost trivial. We simply update the features that we have, and we push the entire data over to the GPU every time. We can take advantage of the stream mode of WebGL. We designate the buffer in stream or dynamic mode. That is a hint to the driver that we're going to update the data quite a bit, and that allows it to speed up the process. But of course, there's also a drawback. And in this case, it's the WebGL 32-bit precision. There's ways around this, and in this case, it's using a local origin. There's no multi-level representation for the data. So if we were to render lines and fields, we may run into some artifacts. Wraparound is much harder to implement than using tiles. But then position itself has to be encoded into like full 32-bit precision. So compared to tiles, at least as far as the position, it takes twice as much as memory. For this particular demo, we've chosen to use the single buffer case. Why? Because the data is highly dynamic and we need a lot of updates. We're only rendering markers. We don't care about fields and lines in this particular case. Wraparound, well, let's say it's a demo, so we don't really care about in this particular scenario, even though there are solutions there too. How can we mitigate some of the shortcomings of using a single representation? So we're simply maintaining a trivial data structure, which is just a map and ID to feature. No R trees, no nothing complicated. We initialize the buffer, in this case the vertex buffer, in a designated stream mode. Every time we're rendering, we're going to upload the entire data over to the GPU. We're using local origin to deal with the 32-bit precision problem. We're going to maybe talk a little bit about that in a later slide. And then we're going to clip the data so that we're going to only visualize and push to the GPU what is visible on the screen. That would allow us to, let's say, not push the data for the entire United States, even though we're zoomed to just the city level. As for the fact that we need to encode position as 32-bit floating points, well, we can pack tightly the other per vertex information, or what we call attributes. This way minimize the amount of GPU memory that each vertex needs to hold. And the last thing, we're going to use a texture atlas that would give a mean to, let's say, put or add all the symbols into a single image and therefore a single texture. And that would allow us to minimize the number of draw calls that we're doing and optimize the performance because of that. The first step is, of course, implementing the layer itself. Here, maybe I should switch over to the IDE itself. So you can see here's my layer. It's extending the layer base class, and it's designated as a custom feature layer. It's consuming a WebSocket. I'm not gonna go to the details of the WebSocket. It's simply a class that allows listening onto a WebSocket at a given URL. And we fit it, and there's a callback that is being fired every time a feature is being updated. And in this particular case, we simply emit it as an event. The layer view is going to listen on that event and take care of storing and rendering those features. We also had a callback when the status change, and this is used by the UI to update the color and the caption of the buttons in this case. Going back to the slide. Um, so when we update those features, each feature is being updated once every 60 milliseconds, and we have 10,000 features. So we're talking about a lot of updates per second. If we were to try to push an update to the GPU whenever each feature is updated, we're going to simply overwhelm the system. So the solution here is to add a update method. This update method is being fired every 16 milliseconds, as you can see here. And then whenever we have a call to feature, meaning that, fired by the WebSocket, then we're going to accumulate those updates in a queue. And then whenever the update method is called, we're going to flush that queue and synchronize the data and then generate the data that has to go over to the GPU. As Dario had already mentioned, the need when we implement a custom layer view, we need to implement the method attach, which is responsible to do all the initialization. Think about it, all the one-time actions that we need to take when the layer initializes. So it means initializing WebGL extensions, creating buffers, textures, and so on. If I go back to the IDE and switch over to the layer view, by the way, notice that the layer view extends the base layer view GL to D that we provide, and go over to the attach method. I'm going to touch about the creating shaders later on, but notice that we're listening to the onFeature event fired by the layer itself, and then goes on to the onFeature method, which adds those features to a queue to update, and then also register a timer method on update, which is fired every 60 milliseconds. We're also reading the information about the cars, and we encode it. I'm going to touch upon that when we're going to talk a little bit about the texture atlas, and also trying to pack this information really tight into each car information is encoded into a single 32-bit integer. Notice that we're using the position or the information of the car and the width and the height of each car symbol, and this all get packed into one integer. This information is going to be used to encode the data of each car into the vertices or the vertex buffer, and then of course we're going to use it later on for the rendering. This is also where we're initializing extension, in this case the VO extension, creating the buffer. Notice again, the buffer is designated with a stream mode. Adding the buffer descriptors, indicating the layout, really. Creating the images, of course, this is for the car texture atlas, and then load it into a texture, and so on. The detach method, basically the opposite of the attach, is really where we're doing the cleanup. This is where we can stop the timer. We can delete the buffers, textures, programs, and so on that we're using in the layer. So already showed you the detach method. And of course, the heart of the layer view is the render method. But before we talk about the render method, we need to talk a little bit about the data that we encode into the GPU and also use to drive the transformation. So in order to mitigate the 32-bit precision issue of WebGL, we're encoding the coordinates relative to a local region. In our case, that local region is the viewpoint of the map, or think about it as the anchor of the display or the center of the display. That, of course, we update every time we need to push a series of updates to the GPU, which is, again, effectively every draw cycle. And so that is used to encode the position. So the position of a car is going to be the vector between the position of the car and the local region. We also taking the extend from the view. We're expanding it a little bit, but then we clip. Sorry, I need to go back. We clip those features or cars that fall outside that visible extend. This is how we effectively make sure that only the data that is currently visible is being uploaded over to the GPU. As for the texture atlas, so a texture atlas allows us to minimize the number of texture bindings, state changes, number of draw calls that we're issuing. And notice here that we simply added all the car symbols into a single image. Each car symbol has its own, think about it, image coordinates, meaning that we know the corner in which it's update, or the upper left corner, and we know the upper right corner, so we know the width and the height of each car in image coordinates. Notice that what we're doing is we're assuming that each such value would take no more than 1 byte. So we have a range of value of 0 to 255, and then we encode that into a single integer. That information is then going to be added to each vertex, and it's part of the way we're going to pick those vertex coordinates. Talking about picking vertex coordinates, well, another thing that we're dealing with is the heading of each car. The heading, of course, is giving it in a range of 0 to 250, 350, 350, 350, 360, my goodness, degrees. But we want to encode into a single byte, so what we're doing, we're normalizing the value, even though we're losing a little bit of precision, but it's good enough, of a range between 0 and 255. And we use that to pack this information together per vertex. And so here we can see the code that encodes this information. It allocates the buffer need to be uploaded to the GPU, then iterate through the cars need to be rendered, and then it computes the vector of the position for each car from the local region to the car's position. It normalizes the heading to a range of 0 to 255. It gets the pre-computed texture information. Again, that is the upper left corner in texture in image coordinates, then the width and the height of each car symbol. And then we're encoding that into the relevant buffers. When we're dealing with WebGL, we have to deal with the shaders. Why shaders? Well, the graphics pipeline is basically built as effectively a pipeline with multiple stages, where each output of each stage becomes the input of the next one. The developer, in the case of WebGL, is responsible to implement 2 stages. One of them is the vertex shader, the other one is the fragment shader. And the vertex shader is responsible to translate each vertex from whichever coordinate space that it is in into normalized device coordinates. And the fragment shader is responsible to color the pixels, or what we call texels. The inputs particular to the vertex shader are buffers, vertex shaders in our case, textures, and uniforms. A uniform, think about it as a constant through the duration of the execution of each shader. Local region, as I promised, we're going to talk about this a little bit. It's simply a mechanism that allows us to mitigate the 32-bit precision issue. Instead of encoding the full coordinate relative to the origin of the coordinate system, we encode it relative to that well-known origin. Of course, we also compute the transformation accordingly. But then when we're translating the vertices, we're really rendering quads. So we're really rendering 2 triangles for each quad. And this is effectively 6 vertices that we're rendering. So the transformation has to work in two stages. One is we need to transform each vertex from what we call pseudo map coordinates, because it's the vector from the local region, to the normalized device coordinate. And then the next step is to move each vertex from the center of the quad to the right corner. And this is what we call the extrude part. So these are the two parts of the transformation. We also need to deal with the rotation. Remember that we packed the heading as a value which span between 0 and 255. So we have to convert that value back to radians in this case. And then we use that to compute a rotation matrix, a 3 by 3 rotation matrix. We simply compute the sine and cosine of the angle. And that will be used in order to multiply the extrude part and rotate the car to the right heading direction. The texture coordinates are given in a range between 0 and 1. Remember that we encoded the absolute position of each car and the width and the height. So we need to translate that and normalize this. We're doing this by passing a uniform that define the width and height of the overall texture. So what we do, we simply divide the position and the width and height by the width and the height of the overall texture, and we get a normalized value that is being later on used in order to sample the texture. When we put it all together, you can in the vertex shader, you can see that we get the attributes, in this case the image size or the width and the height of each car. We convert the heading to radians. We compute the relevant offset of each vertex. The information is given in the range of 0 and 1, so we convert it to a range between minus 0.5 to plus 0.5. And then we simply multiply the position by the display matrix. Think about it as display view model transformation matrix. And then we deal with the extrusion while rotating the data. This is where we're getting the position in normalized device coordinates. We also normalize the texture coordinates, and this is how we generate the position and the output of the texture coordinates. The fragment shader is really the easy part. All we have to do is we use the texture coordinates computed by the vertex shader. That value is going to get interpolated when moving between the vertex and fragment shader. And that allows us to sample the texture in the right coordinate. And that is basically what gives us the color of each fragment for each car. So again, going back to the actual render method. So we got multiple things to do now that we finished going through the shaders. So we know that information needs to be handed over to the shader in the form of vertex buffer. There are some uniforms that need to be passed, the transformations, some scales, and so on. So the first thing we have to do is update the buffer. So we bind the vertex buffer. We pass in the buffer data that's been encoded before. And then we also need to update the transformation matrices. We have two transformations. Again, one translate from the map coordinates relative to the local region, and the other one move each vertex to the right corner, what we call the extrude. So then you can see that we use the local region and the viewpoint to compute where our center is, and we compute the width and the height of our display. And we use that in order to compute the display view model transformation matrix. And we also compute the extrude matrix. And we have to also consider the rotation of the map when we do this. And that is what used to do the drawing. Of course, we also I mentioned that we're doing some scaling, and it's a very, very light scaling in this particular case. We decided to use a logarithmic method just to make things very subtle, not too bold. But that information goes as a uniform, and this is what you can see that at the time we're drawing, we're simply passing this information onto the shader. And then this is how it looks, binding the texture. That is the texture of the car, or what we call the texture atlas. Binding the shader program, binding the buffer, setting the uniforms, the different matrices, the texture, the scale for the icon, and so on, and then dispatch the draw method. We also implement heat test, as I've shown in the demo. There's several ways to implement heat test. It's not there's way more than one technique. The two primary techniques that we're using in the API is through a draw method, where the user is when we're drawing the information using the ID and then reading it back to the system memory, and then looking for the relevant IDs that have been given back, and so on. We use it, both with the vector tiles and the feature layer, and it's extremely accurate. It allows to use very complex symbols, and it works really well. But it requires a dedicated variation of the shader, and require adding a dedicated draw cycle for that. And the readback operation could be slow. WebGL is relatively slow in that respect. The other option is to do it in a geometrical fashion, simply iterate through the features and see which features are under the search area for the heat test. It's pretty fast, but it's quite involved, because we need to consider the size of the symbols, we need to consider the angle of the map, the angle, the heading of the cars. If there is an offset and such, we need to take that into consideration. And so it takes quite a bit to implement that. We've decided to implement the geometrical approach in this particular walkthrough. Again, car symbols are given in pixels. Basically they're image. But we need to again consider the map rotation, the car rotation. And we want to do it right. Even more, when we're doing a hit test, and the hit coordinate is given in window coordinates, and the car coordinates are given in map, so we have to convert at least one to make sure that both are at the same coordinate space. And if we look at it, how and as a matter of fact, maybe I should do it in the IDE and then look for the hit test method. Maybe it's going to be easier. Okay, notice here that of course we need to also consider all the things that we're doing through rendering. The icon ratio. We need to look at the current view scale and the spatial reference, and we're iterating through all the features. And then we can do an early discard. Items that are pretty far away. Oh, notice that we're converting the car position to screen coordinates. So then both the hit test coordinate and the car coordinates will be given in screen coordinates. And then we can early discard cars that are pretty far away from our hitted position. And then we look at cars that are within the tolerance. We are doing a little bit finer computation to see it really fall within the rotated box of the car. And then we're simply looking for the car that is really closest to the hit test coordinate, and this is what we return if we find one. If not, we simply return null. And that is pretty much the end of my demo. I'm going to hand it over to Dario to continue to talk about integration with third-party libraries.
Thank you, Yaron. There is no question that writing custom rendering code is a lot of work. Graphic APIs are often verbose and error-prone. And in the case of WebGL, the bug tools are not as mature as they are on the desktop. Using a WebGL library can increase productivity. In the following, we call helper libraries those that offer thin abstractions on top of WebGL, such as LumaGL, ArcGIS, and Twiggle. On the converse, we call engines those solutions such as Pixi.js and deck.gl that expose higher-level concepts. The choice of a library depends on your project requirements and team expertise. In the upcoming slides, we will see how to implement the same app using straight WebGL and 3 different WebGL helper libraries. In order to be proficient with one of these libraries, the developer still needs a fairly good understanding of the WebGL programming model. Helper libraries are lower level than engines, so they tend to be a bit more difficult to use, but on the other hand, they are easier to integrate with existing code. They typically offer a simplified way to create resources, safer state management, and transparent opt-in and fallback for advanced features. Sometimes they also take care of some of the bookkeeping that normally burdens the WebGL developer, such as associating attribute definition with mesh objects. Here's one of the samples in our SDK. It renders custom markers and animates them using a fragment shader. It is implemented in WebGL. We're going to have a look at how to re-implement some parts of it using LumaGL, ArcGIS, and Twiggle. You can find the original WebGL sample on the SDK of the ArcGIS API for JavaScript and the new implementations on Code 10. Let's start by having a look at importing the libraries. All modern browsers support WebGL out of the box. In these samples, we opted for loading the libraries from a CDN. Import the one you want to use with a script tag and you are good to go. For LumaGL, you will also need to instrument the target WebGL context before you can start. Instrumentation adds WebGL to polyfilling, state tracking, and debug support. Next, let's see how the different libraries approach shader creation. Shader creation is quite tedious in WebGL, as it involves creating shaders, compiling them, linking them into programs, and then retrieve uniform and attribute locations. In LumaGL, one of the core concepts is that of a model, that bundles together everything that is needed to dispatch a draw operation. Shaders can be specified as source strings at model creation. ArcGIS is based on the concept of commands. A command represents a single draw operation, including which uniforms need to be set, but not necessarily their value. As in LumaGL, shaders in ArcGIS are specified as source strings. Commands are created by calling the ArcGIS function. Twiggle has a more procedural interface. Of the 3 libraries, it is the more lightweight and less opinionated of the 3. You create a program by calling twiggle.createProgramInfo. The result is a program wrapped in a program info object that contains some metadata that enable easier use of the created program later on. Next, buffers. In LumaGL, buffers are wrapped into geometries that are then passed into models. You only need to specify the data itself as a typed array, and the model behind the scenes creates the WebGL objects when needed. In ArcGIS, buffers are encapsulated by the command. Just define an attribute section in your command and pass in the data as a typed arrays, or even regular arrays. When possible, ArcGIS will try to infer same defaults for the strides and sides. In Twiggle, you create buffers explicitly by calling createBufferInfo from arrays. The result is a BufferInfo object that contains the buffers and some metadata. Let's talk about uniform setting. All libraries feature automatic type detection for uniforms. You don't have to pick a special function depending on the type of the uniform. LumaGL and Twiggle adopt a similar pattern of offering a setUniforms method. In LumaGL, it applies to the model. In Twiggle, it operates on the program info. In ArcGIS, once again, everything goes through the command. Uniform values must be pre-declared at command creation time. If a command is to be called always with the same uniform, then a constant can be specified. Otherwise, a dynamic uniform can be created using arcgl.prop. The actual value of that uniform will be passed in when the command is invoked. Fixed function state. 2 of the 3 libraries feature safe state management and protection against inconsistent manipulation of the shared state. In LumaGL, you can call the withParameters function and specify some fixed function state and a callback. The state will be changed before the callback is called and restored afterwards. In ArcGIS, once again, this is achieved through sections in the command declaration. The state that you set will apply only to that command and will be reset to default once the command completes. In Twiggle, there is no abstraction over the fixed function state. We are free to set it as needed using standard GL calls. Finally, drawing. All libraries are such that most of the information in the draw time has already been stored in the metadata of the object. You don't need to specify a primitive type and whether the call is indexed or not. In LumaGL, you render by calling the draw method on a model. Usually, you will do this right after setting the uniforms in the callback of a withParameters call. In ArcGIS, drawing happens when the command is invoked. It is at this time that the dynamic uniforms declared with ArcGIS prop can be given a specific value. In Twiggle, there is a function called drawBufferInfo that takes as input a BufferInfo object and renders it. This concludes our overview of these three libraries. Check out the full samples on CodePen. Next, we are going to look at integrations with a couple of engines. Engines are more opinionated than helpers. They provide higher-level abstractions that are fairly easy to understand and use, even for developers that are not familiar with WebGL. But sometimes, because of this higher sophistication, they don't play nice with existing code. Engines normally offer a concept of visual object and container, and a way to group objects together. They usually define a camera model and a way to move a camera around. They support simplified resource loading and garbage collection of unused resources. They support dynamic optimization, such as a way to batch draw calls. Often, they also have a way to create WebGL context and render loop for you. Using an engine, you can get the same result with much less code than using WebGL or even a helper library. Often, the developer does not even have to be aware of WebGL. On the other hand, when integrating with existing code, careful planning is needed. For starters, normally you wouldn't want an engine to create its own WebGL context and render loop. They should instead be sharing them with the code that is hosting them. For the next sample, we will have a look at deck.gl. Deck.gl is a WebGL-powered visualization framework for large-scale datasets. In this sample, we will show how to overlay one of the standard layer types offered by deck.gl on top of an Esri base map. It is a grid layer that is aggregating point features and using a color ramp to visualize how many features fall into each cell. Esri has worked with the Pixi.js Foundation to publish the deck.gl ArcGIS NPM package. This package enables easy integration of deck.gl with the ArcGIS API for JavaScript. Internally, it uses a custom layer view just like the ones we created in the previous samples. To use deck.gl, we import the main deck.gl module from the CDN, and then we import the deck.gl ArcGIS plugin and finally the JS API as usual. In this sample, we will be fetching data from an ArcGIS feature layer, we will reproject it using the projection engine, and we will render it with deck.gl. We use require as usual to load the JS API modules that we need. The feature layer will not be added to the map. We will only use it for querying. Querying a feature layer returns a promise, which we store into a local variable. When loaded from the CDN, deck.gl is available as a global deck object. In order to load the additional classes provided by the deck.gl ArcGIS plugin, we need to call deck load ArcGIS modules. This call, too, returns a promise. Finally, since the feature layer that we are querying is Web Mercator, and deck.gl expects longitude and latitude, we will need to reproject the queried data. For this, we need the projection engine. Because the way it is implemented, the projection engine needs to be loaded with a call to load before it can be used. This call also returns a promise. We then wait on these three promises using promise.all. When they resolve, the callback receives the return features in the result variable, and the deck.gl ArcGIS classes needed for the integration in the ArcGIS variable. The first thing that we do is reproject the points to WGS 84. Then we create an instance of ArcGIS deck layer. This is an ArcGIS layer that can be added to a map and that can host deck.gl layers and render them using deck.gl. Basically acts as a pseudo group layer for deck.gl layers. In this sample, we only add a single deck.gl layer called screen grid layer. The most important property that we must define when creating a screen grid layer is the getPosition method that must map an Esri point geometry object to a longitude-latitude pair, which is what deck.gl expects. The instance of ArcGIS deck layer can now be added to a map. It will behave just like any other ArcGIS layer, but we'll use deck.gl internally to render a screen grid layer. The sample is available on CodePen. Check it out for more details. For the last sample, we are going to integrate Pixi.js. Pixi.js is a high-performance, fairly high-level 2D engine. We are going to see how to work with sprites in Pixi.js, position them on the map, animating them, and we are also going to see how to load an extension for Pixi.js called Pixi Particles that adds support for particle systems. We are going to import Pixi.js and Pixi Particles and then the JS API. Please note that this integration is quite experimental. Use caution if you decide to use this technique in production. To keep things simple, we'll be creating all the Pixi resources that we need in the attach method. We create the Pixi render, which is the object responsible for rendering the objects. We also create a sprite and particle systems. We'll update their position as the view state changes. In a real-world scenario, the layer view will probably be listening to the layer, but in this sample we want to focus on using Pixi.js. Part of the contract between map view and the custom layer views is that the custom layer view must render in the frame buffer that is bound when the render method is called. However, Pixi.js does not support rendering to an externally created FBO. For this reason, in order to integrate Pixi.js, we need to set up an off-screen surface that Pixi.js can use. We do so by creating a render texture, a Pixi.js abstraction over a frame buffer object. Then we create, using raw WebGL calls, a full-screen quad and a texture mapping program that we will use to overlay the content of the render texture on top of the map. All of these will take place in the render method. First, render with Pixi.js. Second, recover the rendered image. Third, composite it with the map view. It is a common way of integrating two rendering engines. In the case of Pixi.js, we will need a little egg to recover the rendered image so that we can draw it. Let's start with the easy part, rendering with Pixi.js. We position and animate the object as needed. We use the toScreen function to keep the sprite and the particle system anchored to the map. Then we call the resize function on the renderer and the render texture. This is to account for possible changes in viewport size, for instance if the user resizes the browser window. Notice how we include the pixel ratio in this computation. We do this to account for high DPI displays. All the Pixi.js rendering code is wrapped between calls to render or reset. This shields both the map view and Pixi.js from working with an unknown WebGL state. After Pixi.js is done rendering, we recover the actual WebGL texture that is contained inside the render texture, and we overlay on top of the screen using the program and the quad that we created in the attach method. This concludes our presentation. Check out the samples on CodePen for more details on these and the other samples that we discussed. All the samples that I presented are part of a CodePen collection, while Yaron's awesome card tracking app is available on GitHub. Also on GitHub you can find the streaming server that is required to run the app. The streaming server is based on some original code by our colleague Matthew George. Thank you, Matthew. Both the app and the server are also deployed as live demos, so be sure to check them out. Thank you so much for joining us today. Happy coding and good luck with your custom visualizations.